Your eyes don't deliver reality. They deliver a best guess your brain can act on quickly. Illusions are not bugs. They are windows into the rules your brain uses to turn light into meaning. If the rules fit the scene, perception feels effortless. If the rules misfire, you get an illusion and a chance to see the system at work. Start with context. In the Müller Lyer illusion, two equal lines look different lengths when you add inward or outward arrowheads. The brain treats those angles like depth cues, as if one line is farther and needs to be scaled up. In the Ponzo illusion, converging rails imply distance. A bar near the horizon looks longer than an identical bar in the foreground. Your visual system is not measuring pixels. It's correcting for an assumed 3D world. Now brightness and color. In the checker shadow illusion, two squares are physically the same shade, but the one in shadow looks lighter. Your brain applies a rule. A darkened surface in shadow should be adjusted upward. The result is a stable world despite changing light color constancy. Yet the same rule makes two identical tiles look different. Simultaneous contrast plays a similar trick. A gray patch on a dark background looks lighter than the same gray on a light background. Edges and surrounds reshape perception, not because your eyes are weak, but because the brain prioritizes differences that matter for object boundaries. Filling in shows up when the brain completes patterns that aren't physically there. The Kanizsa triangle is three Pac-Man shapes that make you see a bright triangle floating on top. There's no triangle, but your brain prefers simple, coherent shapes. Even your blind spot is filled with invented background. You don't notice because perception is designed to prioritize coherent scenes over perfect pixels. Motion reveals opponent dynamics. Stare at a waterfall or a moving pattern for 20 seconds, then look away. The world seems to drift in the opposite direction. Neurons tuned to one direction fatigue. Their opponents dominate for a moment, so you see opposite motion. The wagon wheel illusion in video lighting can make a spinning wheel appear to reverse. Temporal sampling and neural tuning interact with expectations about time and motion. Why does this happen? The simple answer: efficiency. The brain runs a prediction model. Top-down expectations meet bottom-up signals, and the brain selects the most probable explanation. Lateral inhibition sharpens edges by suppressing neighboring signals, making contrasts pop. Bayesian priors bias perception toward what usually happens in natural scenes: overhead light, stable objects, smooth motion. These priors make vision fast and robust. They also set traps in rare or contrived contexts, which is exactly what illusions exploit. What does this mean outside the lab? In design, trust your users, not your eyes. A color that pops in isolation may vanish next to a saturated banner. Test icons in their actual surrounds. Check legibility under different brightness and contrast levels. In photography or e-commerce images, be careful with shadows. Subtle gradients can make identical products look like different colors. In UI, avoid relying on color alone for meaning. Use shape and text labels to add redundant cues. In everyday judgment, remember that first impressions are often predictions, not measurements. Lighting, angle, framing, and context can change what is seen. Eyewitness confidence can be high even when perception was constrained or biased by context. In marketing, framing effects are cousins of illusions. A was $199. Now $99 frame changes perceived value even when the object hasn't changed, because the brain encodes the relative contrast. How to defend yourself? First, change the context and check again. Move the object, change the light, step back, zoom in. If the perception changes, you were looking at a guess. Second, use multiple cues. Color plus text, size plus position, motion plus shape redundancy stabilizes interpretation. Third, slow down when the stakes are high. The fast system is useful but fallible. The slow system can audit. Fourth, get an external check. A ruler, a color picker, a friend's view, a device screenshot under different brightness, anything that pushes beyond your internal guesses. A few quick demos you can try. Draw two equal lines, add opposite arrowheads, and watch them change length. Place a gray square on a black background and on a white background, then compare. Stare at a moving GIF for 20 seconds, then look at your hand. It may seem to ripple. Cover the rest of the checker shadow image and slide a window over the two target squares. They will match when the misleading context is hidden. Each demo removes or alters context, and each time the perception shifts, because perception depends on what surrounds the target, not just the target. The deeper lesson is optimistic. Illusions don't prove that perception is useless. They prove that perception is optimized for action, not accuracy at every pixel. Your brain compresses and corrects to give you a stable, useful world. When that optimization meets an unusual pattern, the assumptions show through. That's the moment to learn. Ask, what rule did my brain apply? What cue did it weigh too much? What context was misleading? Once you know the pattern, you can design around it, communicate more clearly, and make fewer rushed mistakes. Perception is a story your brain tells to keep you safe and effective. It is fast, predictive, and good enough most of the time. But when the story bends, when lines stretch, colors drift, motion lingers, you now know where the seams are. Change the context. Add more cues. Slow the snap judgment. And when something looks obviously true, give it one more look in a different light.